Significant figures is a huge topic in all realms of science as well as math. And significant figures in a nutshell tell you the precision to which you may report an answer. This becomes exceptionally important in laboratory settings. Here's an example. Let's say you're using a balance, and the balance reads out the mass to the 100th place. But in your lab notebook, you record the balance to the 1000th place. Do you really know what the mass is to the 1000th place? Or are you lying and making it up? Not sure. Here's the basis of using significant figures. It allows you to report to the greatest precision possible without incurring too much error or lying about figures you can't actually report. So let's look at the rules. Identifying significant figures and numbers has some different complex rules. First of all non-zero digits are significant. So for example, in the number 7,534, all 4 digits are significant. And by the way, significant figures can be expressed as Sig Figs or S.F. Okay, so if I write S.F or Sig Fig or something like that, I need significant figures. So in this case, the number 7,534 has 4 significant figures, and that's all we need to know about non-zeros. Zeros, on the other hand, are where things become a little bit confusing. Zeros may or may not be significant, and there's a few cases where we need to be able to discern whether they are or are not. Let's look at it. Leading zeros are not significant. So, for example, 0.00255 has 3 significant figures in this number: the 2, the 5, and the 5. These zeros are merely telling me, right, that this number doesn't start until the 1000th place. That's all they're doing. They're place holding. They're not necessarily a specific measured value. So, another way that we can write these things to show, that there are 3 significant figures is we can convert to scientific notation, right? So you can also write this number as 2.55 times 10 to the negative third. Cool. Now, if the number contains a decimal, we say that trailing zeros, so imagine if this number had zeros that came after this 5, those would be significant because we know that it's exactly 255,000,000. That's an exact measurement. Trailing zeros are significant in the case of a decimal, but if trailing zeros occur without a decimal point, the desired number of significant figures is ambiguous, right? And we have a way to solve that problem. However, let's look at the 2 examples. In the number 7,580.00, there are 1, 2, 3, 4, 5, 6 significant figures because those trailing zeros are found in a number that has a decimal. However, in the number 8,000, it's ambiguous as to how many significant figures there really are. There is a way, however, to fix these ambiguous numbers, and it's the same thing that we did up here to change the notation to scientific notation to show the amount of significant figures here. For example, if we wanted to write 25,000 in a way that showed that it was exactly 25,000, but did not have an ambiguity in terms of significant figures, we would convert to scientific notation, right? So instead of 25,000, here, right, the sig figs is ambiguous. So, convert to scientific notation, we get 2.5 times 10 to the 4th. Now we can see that there are, in fact, 2 significant figures. The last case for zeros is if there are internal zeros, zeros sandwiched by non-zero numbers, right? So these 2 zeros in between this 5 and this 8, this 0 in between this 6 and this 5, things like that. Those are always significant because we know those are in fact zeros because we have numbers after to show where the measurement continues. So for practice, go ahead and identify the number of significant figures in the following quantities. And pause the video and go ahead and try and do this before I give you the answers. So I hope you tried these, and we're going to go through them pretty quickly. In the event that any of these would be ambiguous, though, make sure that you convert to scientific notation to show how many sig figs there would be. So we're going to start over on the left, and we're going to go left to right. To start with 700, remember there's no decimal here, so it's ambiguous to as the number of significant figures. I'm just going to put ambiguous under the 700. We're going to say convert. Right, so 700 equals 7.00 times 10 to the second, right? So we could say that's 3 sig figs, or you could just say 7 times 10 to the second, which would just be 1 sig fig. Either way, I think I would personally choose this, but I could see where you would get the idea for these zeros. Remember, it's ambiguous. All we really know is that this is a 7, so we need to write it this way. Let's go on to the next problem, 2505.00. So a couple things, right? You see a decimal place, so you know that the trailing zeros are significant, and the zero is internal, so it's significant, so we're just going to count up the numbers, right? 1, 2, 3, 4, 5, 6, right? So we know this is 6 sig figs. In the next number, we do have a decimal point, right? But you see these zeros are leading, right? So that means they're not significant. They're just placeholding, saying that our first digit starts at the hundredths place. So we would have 1, 2, 3 significant figures here. In the following number, we see we have two things. We have an internal zero and we have trailing zero with a decimal point. So you're going to use that same process you used for this number right here. And this is going to be 1, 2, 3, 4. So 4 sig figs. And for the last one, this is a way that we can write numbers with a decimal point right here at the end. Even though there's nothing over here, this decimal point does indicate that these zeros are significant. So there's 1, 2, 3, 4 sig figs in this number. So that's the first page of significant figures. And we're going to move on to talk about a couple rules and calculations with significant figures to make sure that we're reporting answers to the precision that we are allowed. So there are a lot of specific rules, but really it boils down to two different rules. One rule that applies to addition and subtraction, and another rule that applies to multiplication and division. We're going to talk about addition and subtraction first, though, and I like to call this rule, and I am using the terminology from a very dear friend and professor. This is what is called the decimal point rule. The decimal point rule. And the decimal point rule says, and this is just my term for it, there's really a different term for it, which would be just the rule for addition and subtraction, but anyway, that's neither here nor there. The decimal point rule says that you can report your answer to the precision of your least precise value. And that's a lot of words to just say, look at all your numbers. The one with the least amount of places after the decimal or before, right? The least amount of places with reported numbers you can report to, right? So let's do an example problem. If we did 0.5 plus 0.00255, and if you want to read this blurb right here, this is for you to read. I'm not going to read it to you because it's there and it's on a screen, and you can pause the video to read it if you want. So if we do these numbers right here and we just add them, right? We're not going to subtract anything. We're just going to add, right? So if we go 0.5 plus 0.00255 plus 0.25, right? We get a number of 0.75255. And that's great. But in this case, right, we need to look at the lowest amount of significant figures that we have. The lowest amount of significant figures that we have can be determined by just counting up all the sig figs in the numbers, right? So if we start with this 0.25, right, there's a leading zero with a decimal point, so that's not significant, 1, 2. So that's 2 significant figures. This next number has these leading zeros with the decimal again, so 1, 2, 3. 1, 2, 3. Wanted to make sure the pointer worked. 3 significant figures, right? And this last one has one significant figure. Now, I want to point something out. When it comes to the decimal place rule, okay, the step that we just did, don't do that. If you wrote this down on a piece of paper that you're taking notes on, cross it out, scribble it out. You don't need to do this. You're doing too much work and you're thinking too hard. Don't worry about it. We're going to erase it, right? This is going to become relevant later, but I just wanted to make the point that if you start counting up significant figures for addition and subtraction, you're not on the right track. What you need to do is you need to find the number with the lowest precision. This number goes to the tenths place. This one goes to the tenths, hundredths, thousands, 10,000, 100,000ths. This one goes to the hundredths place. So we can report our answer, that was a very poor line, to the tenths place. Because this number is done after the tenths place. So what we would do is we would need to round, right? That's 0.75255 to the tenths place, right? So our answer would be 0.8. That's the addition and subtraction rule. So don't count up sig figs for addition and subtraction. Just say, what's the lowest precision? This is the lowest precision, so I can only report my answer to the tenths place. Now we're going to get to count up some sig figs for multiplication and division. So multiplication and division have a different rule. This is called the Sig Fig Rule. And basically it means you can have as many sig figs in your answer as the lowest number of sig figs in one of your values, right? So let's do a practice problem, right? So we're going to multiply 5.5 and 3. 5.5 has 2 sig figs. 3 has 1 sig fig, and I'll write that in for you. So if we do 5.5 times 3, we get 16.5. And that's great. But we can only report our answer to 1 sig fig. We can only report our answer to 1 sig fig because this number right here only has 1 sig fig. So this would actually be rounded up to 20. Right? 20. And if I was going to be really accurate, what I would do is I would write 2 times 10 to the first. Because 20, and I put this decimal point here and I shouldn't have. Right? If I just write 20, that's ambiguous. Right? So I don't want you guys to think too hard. If you do this problem in a Gen Chem 1 class and you write it as, so you do that and you go, we get it. We get it. But check with your professor to make sure they don't want you to go all the way over to scientific notation. Let's do one more problem. We're going to do 81 divided by 4.0. Okay? When you do this problem, you get 20.25. Now, you'll see that in our numerator we have 2 sig figs, and in our denominator we have 2 sig figs. So we can report our answer to 2 sig figs. That means we are going to round it at 2 sig figs, right? So we can count these sig figs. We're going to round these off to that place. So since it's 0.25, it's just going to be 20. Pretty cool. Pretty cool. And you can put a decimal right there because you do get 2 sig figs. So there's some practice problems on the next page that I encourage you all to try. I am going to pause the video on my end of the things, and you're going to do that as well. When you keep going through the video, at some point in the very, very near future, the answers are just all going to appear. So I will not work through these as I work through the other ones, but you can use this as practice and then check your answers with mine. Good luck. So I hope you tried these problems and you got similar things to what I got. I'd like to draw some special attention, for some reason that sounded weird, to this number 2 problem right here. So you see we have 8.50 minus 2 plus 10, right? We see our least precise number in both this case and this case is reported to the ones place. In this case, it's kind of ambiguous, but we basically call it the ones place since we have 2. So we'd see that 8.5 minus 2 is 6.5, plus 10 is 16.5. So we're allowed to report to the ones place, which means we have to round off here, right? So we're allowed to report to the ones place, right? We're allowed to report to the ones place. Now, there's a funky rule with significant figures and rounding that I feel like it's worth mentioning right now, just really briefly. Check with your instructor whether they are going to lecture and or assess you on this rule to see if you have to look into it some more. But I'm going to talk about it briefly. Basically, at some point back in the history of science, somebody decided we like even numbers. So, in the event that we are rounding, right? So everyone tells you if it's 0.5 or greater, you round up. If it's 0.49 or lower, you round down. Not always the case, right? If we have an even number, like we do here, and it's 0.50, okay? It's halfway to the next number and absolutely nothing more. Not 0.501, not 0.50001, nothing. 0.50 and nothing more. It is exactly between 16 and 17. We want to keep the ones place digit even, okay? And you're going to round that 0.50 back down to the even number, okay? So, just to recap, right? Just to recap, I'm going to move the screen down here. I'm actually going to copy this, so it's going to be 2 prime. It's going to be 8.50 minus 2 plus 10 equals 16.50. I'm going to put an arrow. I'm going to say ones, and it's going to be 16. Okay. So, rounding rules, right? Right? If you have an even number, right? If you have an even number, such as the 6. And it is followed by, or is, 0.50. Actually, we're just going to say halfway to the next number. Sorry, next number. Okay, which would be odd, right? Round down. So, for example, right, if we have 8.50 and we can report to the ones place, right, it'd be 8. Let's say we have now 9.501 and we can report to the ones place. It would be 10. Right, it'd be 10. Okay, and we could even put a little decimal right there to show that it's reporting to the ones place and it's not ambiguous. But needless to say, if you have exactly half and nothing more with an even number, actually, let me redo this because I'm not getting to odds yet. Let's go 8.501, and that's 9. Sorry, miswrote that. I'm a little bit farther ahead on my notes than I am on the screen. There we go, 8.501, rounding to the ones place would be 9. Okay, so for even numbers, remember, if it's exactly halfway, you're going to round back down to the even. If it's even a little bit over halfway, you're going to round up to the odd. Okay, this is part 1. This now is part 2, right? If you have an odd number, halfway between an odd number and the next highest even number would round up. Okay, so halfway, I'm going to put exactly, rounds up to the next even. So, for example, right, 9.50, we're going to round to the ones place, would be 10. 9.501, which we round to the ones place, would also be 10. And we'll put the decimals there just to show that it's not ambiguous. Okay, so that's the difference between rounding at even and odd numbers. Okay, so back to the question, right, and we can erase this because I did it somewhere else on the screen. Back to the question, though, we see that we have an even number. It's exactly halfway between, so it rounds back down to the even. So a little rounding rule right there. Anyway, I hope this significant figures video helped you understand more about significant figures, cleared up that rounding stuff a little bit, got through the calculations, and helped identify sig figs. We'll see you next time.